cosines, can you make it so you're good at moving things around without typing those ugly numbers in your calculator? So when we were looking at this one right here, okay, I mean, that's a lot to keep track of in your head. And we have this compulsion that we always want to go through and, hey, if I see 4.5 squared, I want to type that into my calculator. So I've got a decimal for that, okay? As much as you can get away from that, it would be a really good idea, because the further you go in math, the more we just kind of compartmentalize and say, oh, that's just a number. I don't care how ugly it is. It's just a number, okay? We worked with logs in this class, didn't we? Yeah. Remember those logarithm problems where we had stuff like that, where we said, hey, this is just a number, okay? If you write it log of 7, okay, that's 4 characters. If you type it into your calculator, it's a big, long, ugly decimal, okay? You'd have to write down over and over and over, or you'd have to round and then introduce some error. So getting used to the idea that, hey, that's just a number. I'm going to treat it like any other number and be able to move it around like you would any other number. That's a really valuable skill, okay? All right, any questions? Okay, let's go ahead and remind ourselves of what we were talking about with 6.3. We're talking about vectors. And just in the little bit of work that we did so far, we introduced a whole bunch of vocabulary. We were talking about initial points and terminal points, tip and tail, magnitude, and direction angles, and all sorts of stuff. We talked about how on this example that starts at 0, 0 and goes to the point 3, 4, how we can represent that geometrically with a directed line segment. So we draw a line and would put an arrow on the end so we can tell what direction it's going. We talked about how we could find the magnitude of this, thinking in terms of the Pythagorean theorem. So we took this leg and squared it, that leg and squared it, because this was the horizontal piece. This is a vertical piece, and those do meet at a right angle. Okay, so we found that. And then we talked about how we could find the direction angle, and we could use sine or cosine. But we talked about how it might be a good idea to use these two sides, the opposite side, the vertical side, the y coordinate, if you want to think of it that way, and the x coordinate right here, the one that's running in the x direction, and then use tangent and tangent inverse, okay? And it kind of said, you know, you've got to be careful with this, because tangent inverse, think about the range for tangent inverse. It's going to give you answers between negative 90 and 90, but we're usually going to want to have things between 0 and 360. So this is a good way to figure out the size of the reference angle, but if you're going to figure out the actual direction angle, say we've got one over here, you'd have to be able to compute that right there. So reference angles, like we've talked about before, are going to be really important, okay? Any questions about the stuff we talked about or introduced last time? Okay, so the thing we left off with is we were talking about how we can tell if two vectors are equal. And we said the only way they're going to be equal is if they have the same magnitude and the same direction. Same magnitude and same direction. Both of those have to be the same. So we're going to draw a couple of vectors here. So we're going to draw a vector AB again. So I'm going to go over 1, 2, 3 and up 4. Okay. Draw an arrow on the end, and that's vector AB. Okay, so I'll put that line over the top of it. I'm going to draw a vector CD. So it starts at C and ends at D. So this is 4, 7. So 4 and 7. 1, 2, 3, 4, 5, 6, 7. So we're right here. And I'm going to change colors for this. So here's C, and then D is at 1, 3, so 1, 3 would be right here. Put an arrow on that, and that's CD. Let's see, the next one is 2, negative 1, 2, negative 1, and we're going to go to 5, 3, so 5, 3. That one right there, and that's vector EF. Put that little vector over the top of it. And then I've got this last one, GH, and GH starts at negative 4, 1, so negative 4, up 1, that's where it starts, and it goes to negative 6, 4. So negative 6 and 4, that's going to be about right there. We'll kind of eyeball that. And again, it's going from G to H, so it heads off in this direction right there. So that's how we'd represent that vector. And again, I can label that as GH, like this. That looks kind of ugly. Okay. Any questions there? Pretty easy, right? Okay, let me ask you this. Can I do this? Okay, this is H and this is G. So could I say HG and put the arrow over it like that? Why not? Brandon? The way you write it is the direction that it goes in, okay? So this would indicate that the tail is H and it goes in the direction of G. It would be heading in the opposite direction, right? Okay, still in the same place, but the arrow would be in the other end, so it would indicate that it's heading off in this direction rather than heading off in this direction. Make sense? Okay, so let's take a look at those, and it says state which vectors are equal. Okay, so let's look at GH. Is there any way GH is like these other three? There's no way, okay, because it's shorter, doesn't have the same magnitude, and it's pointing off in this direction over here, right? So there's no way that one's equal. Of these three that are left, are there any that are equal? Okay, anyway, CD is equal to the two of these. Okay, what's the reason there? Okay, clearly heading in the other direction. Okay, even if it was off just a little bit, I mean, it's pointed the other way. These are pointed northeast, that one's pointed southwest, right? So there's no way that one's going to be equal. Okay, we could check the magnitude on each one of them and see if they're the same. Now, let's go ahead and do that on this one because A, B, and E, F look like they're pretty good. Now, remember, vectors are the same, they're equal if they have the same magnitude and the same direction, if they're headed off in the same direction. And by direction, we would mean direction angle. So let's stop and think about this. We don't necessarily have to figure out the angle. We could do it this way. How far do I have to go over here and then up here to kind of figure out how far horizontally and how far vertically? In other words, kind of what the slope is there. Over 3 and up 4, right? Isn't that exactly the same thing as what we had here, over 3 and up 4? Okay, so wouldn't they be headed in the same direction? And if the horizontal leg, if you wanted to think of it that way, is 3, and the vertical leg for each one of those is 4, wouldn't the magnitudes for both of those be 5? They would, okay? So this is a really important point. It doesn't matter where a vector is. What matters is how long is it and which direction is it pointed in. What is the magnitude and what is the direction? So those two are equal, okay? And I want to show you something, okay? Notice that we can slide a vector around and it doesn't change the magnitude or the direction. So what if I wanted to take this one right here? What if I wanted to take EF? And what if I wanted to slide it right on top there? I'd need to back this one up 2 and go up 1. So back 2 and up 1. If I back this one up 2 and go up 1, wouldn't that put, oops, let me change colors here. Wouldn't that put EF right on top of AB? And then wouldn't we be able to say, yeah, no duh. I mean, we could bring a second grader in here and they'd be able to tell us that those two are exactly the same, right? Okay. What I just did there is made what we call a position vector or a radius vector. And the easiest way to make comparisons is move it so each tail is at the origin. And that makes them easier to compare because they all start in the same place. If they start in the same place, then it's going to be easy to tell if they're the same length and if they're pointed the same direction. So if I were to zoom in on this one, and let's say I had one that was like this. Went to there. Let's say it looks like it's exactly the same length, but you can see a little bit of light in between the two of those. It may have the same magnitude, but then you can look at it and say there's no way they're heading in the same direction. Even if they're just slightly off, you'd be able to tell, right? So that's called a position vector or a radius vector, and those are really useful because it's easy to compare those, okay? So this idea leads us to the idea of, it's called component form. Component form. So component form is really useful because it allows us to write a vector using just two pieces of information. And those two pieces of information are a horizontal component and a vertical component. So component form looks like this. Okay, instead, I know we're working on the XY plane, or it looks like we are. Okay, so instead of using X's and Y's, we change letters and we call them A and B. And instead of using round brackets or parentheses, we use these angle brackets. So I'd have an angle bracket A, comma B, angle bracket. Okay. And A is the horizontal component and B is the vertical component. So it's set up a lot like we use X and Y coordinates. And the way we tell the difference between an XY pair and an AB component form of a vector is those angle brackets. And component form is really, really useful. Okay, there are other ways of depicting them. We can use pictures and stuff like that. But component form is very useful because you can have, it's easy to put them into computers and stuff like that. Okay, so we're going to take this vector AB that goes from -2, -1. Yeah. Oh, yeah. Oh, I'm sorry. I've got a typo here, don't I? Okay. B is the vertical component. Yep. Sorry about that. Thank you for catching that. I will have to fix that. Thank you very much. Vertical. Okay. All right, so here's what we're going to do next. In this next example, we're going to take vector AB. So this is a new vector AB. I know I had one up above. We're going to take the vector that starts at -2, -1 and goes to 2, 4. Okay, and we're going to put that in component form. So let's draw what this looks like first of all. Okay, so I'm going to change colors here. This goes from -2, -1, -2, -1, and 2, 4. So over 2 and up 4. So right here. This is what that vector looks like. Okay, I want to make this into component form, so there are a couple different ways that I can do this. Okay, I could physically slide it over and I could think, okay, I need to slide it to the right 2 and up 1. So I'd slide it to the right 2 and up 1. That means I need to slide this to the right 2 and up 1, and that puts me right here. So here's my new copy of it. It's exactly the same length. It's headed off in the same direction. Again, you can slide vectors around and it doesn't change the magnitude or the direction. So these two are equal to each other. Okay. And then I could go through and I could count, okay, how far over did I go and how far up did I go so I can find a horizontal and a vertical component. Okay. Or the easiest way to do this, the easiest way to put this in component form is to subtract the tail from the tip. So I'm going to take 2, 4, and I'm going to subtract -2, -1. Now watch what happens if I do that. What is 2 minus -2? 4. And what is 4 minus -1? 5. I'm going to put brackets around that right here, and I'm going to blow this up so we can take a good look at this. How far over do I have to go to get to that point right there? I start at the origin and I go over 1, 2, 3, 4. And I go up 1, 2, 3, 4, 5. Okay? So the horizontal component is 4 and the vertical component is 5. Because if you think about where these points were, this was -2, -1, and this was 2, 4. If I moved everything over 2 units and then up 1 unit, that would put this point right here at the origin where we want it for a position vector. And if I take 2, 4 and I move it over 2 and up 1, that's going to put this point right here at 4, 5. So if it starts at 0, 0 and heads to 4, 5, it's really easy to tell, hey, the horizontal component is 4 and the vertical component is 5. Does that make sense? So the easiest way to take 2 points, a starting point and an ending point, an initial point, a terminal point, a tail and a tip, the easiest way to put that into component form is to take the tail and subtract it from the tip. Make sure you do it in the right order. If you don't do it in the right order, you're going to get the answer backwards. Okay? Everybody good there? Okay, so let's go back up here and let's write each one of these in component form. These are all the tips. These are all the tails. So on this one right here, how could I write the vector AB in component form? Tip minus the tail. 3 minus 0, 4 minus 0. Horizontal component of 3, vertical component of 4. Make sense? Tip minus tail. Minus 3, minus 4. That was CD. Now, do you notice anything about the two of these? Exact opposite, right? Because it was going in the opposite direction. Okay, let's take this one. Here we're going to end up with 3, 4, right? And isn't that the one that we said was exactly equal to it? And then this one right here, we're going to take -6 and subtract that, so that's going to give us 2. And then we're going to take this and subtract, we're going to end up with a 3. Oh, you're right, it would be -2, thank you. Yep. Okay, any questions? Sure? Okay, I want to just demonstrate something. Okay, for this one right here, we're going to go over 3 and up 4. It's heading off in this direction right here. For this one right here, remember these are position vectors or radius vectors, we'll call them sometimes. We're going to go back 3 and down 4. Back 3 and down 4, it's heading off in that direction. Exact opposite directions. This one right here, 3, 4, right on top of that one. And this one right here, -2, so we're going to the left and up. So we head off like that. Okay? See how these vectors right here, if we move them so their tail is at the origin, if we make them position vectors, it's very, very easy to compare them. Okay? Component form is unbelievably useful, especially in higher mathematics. Okay? All right, everybody good? Okay, go ahead and flip the page over. Okay, so again, if we've got it in component form, it's often useful to find the direction angle. The direction angle of a vector is of a vector measured from standard position. In other words, the positive side of the x-axis. And the direction angle is always going to be between 0, and if we do it in degrees, 0 and 360 degrees. Okay, and please underline this. We often use reference angles. So we're going to find reference angles, and then we've got to make sure that once we put it in standard position that we've measured the angle correctly. Okay? So it says find the magnitude of AB, written as, remember we can use absolute value for that, and the direction angle for the example, in example 3. So this one right here, this is what we want to find. Okay? We want to find the magnitude and we want to find the direction angle. So if that is like this, and the horizontal component is 4 and the vertical component is 5, how do you find the magnitude? How do you find the magnitude of AB? We kind of talked about it yesterday, and we're going to come up with a formula for this in just a second. So if this is our vector, if our vector is 4, 5, how do you find the magnitude? How do you find how long this is? Pythagorean theorem, right? So we're going to take the horizontal part, the 4, we're going to square that. We're going to take the vertical part, which is 5. We're going to square that. And then what are we going to do? We're going to take a square root. Okay? So that's going to be 25 plus 16. So that's going to be 41. What's the square root of 41? 6.4-ish. Okay? So approximately 6.4 is the magnitude. Okay? Now, what if I want this angle right here? What did you say? Okay, we're going to use tangent. The tangent of theta would be equal to, okay, the vertical. Think of it, we learned y over x. This is vertical over horizontal, so this is going to be 5 over 4. So theta is going to be equal to the tangent inverse of 5 over 4. And if somebody could throw that into their calculator for me. Again, expecting an answer either bigger or smaller than 45 would be great. We're expecting an answer that is bigger than 45 because that opposite side, that vertical component is bigger. And what do we end up with? 51.3 degrees. So I've got a magnitude and I've got a direction. So magnitude here and direction here. Okay? Now, if we can do that for that problem, then we should be able to do that for any vector AB. So if the horizontal component is A and the vertical component is B, how do I find the magnitude of vector AB? What would I do? Yeah, square root of A squared plus B squared. Same thing we did up there. And if I wanted the direction angle? Tangent inverse of, think about it for a second, don't say anything out loud. Tangent is always the y over the x, or it's the over, what are we going to write here? B over A, because B is the vertical and A is the horizontal. Now, these are formulas that you can find in your book, or at least the ideas would be represented by formulas in your book, but I want you to take a good look at this. For the examples that we've done so far, everything was in quadrant 1. Everything was in quadrant 1. Do we have to be careful about these at all? Do we have to be careful with both of them or one of them? Okay, well, let's take a look. Let's do this problem right here. So this is 6, 4, and we want to find the magnitude and the direction. So we can get an idea of what this looks like. 6 and 4. That's 6, that's 4. I can find the magnitude. It's going to be the square root of, according to our formula, we square the horizontal, square the vertical, take the square root. So I'm going to get the square root of, that's a square root of 36 plus 16, so square root of 52, roughly 7.21. 7.21. That is roughly what the magnitude is. If I want theta, if I want the direction angle, our little formula says we can do tangent inverse of vertical component over horizontal component. So that would be 4 over 6. We're expecting an answer smaller than 45, right? Because the opposite side is smaller than the adjacent side. And what did you get? 33.69? 33.69 degrees. Okay, everybody good there? Okay, does that look good? Think it works? Okay, will it work for this one? Notice that we've got a negative here. So on this problem, I'm going to change colors. So -5, we're going back 5 and we're going up 9. So a little bit taller. So here's our vector. -5 here and 9 here. So the first worry is if I'm finding the magnitude, we said we should take the square root of -5 squared plus 9 squared. Does the negative mess anything up here? Why not? Because it's squared, right? So we get 81 plus 25, so 106. Square root of 106, roughly 10.3. So the magnitude is roughly 10.3 on that one. Okay. Theta, according to our little formula, should be tangent inverse of vertical over horizontal. So we're going to put the b over the a, 9 over negative 5. Are we expecting a pretty big angle? I would be. I'd be expecting a pretty big angle. What does your calculator say? Thank you very much. Negative what? Negative 60.94 degrees. Okay, now, don't say anything out loud. Take a look at this for just a second. We were hinting at the idea that, yeah, maybe these formulas work, and they work really well in the quadrants we've been working in. But when we run into something like this, we've got to be a little bit more careful. Now, does anybody have any concerns about the magnitude? Doesn't that look like a little bit bigger than 9, 10.3? Does that look okay? No problem there. The formula that you came up with for the magnitude works perfectly, and you'll find that one in your textbook. The formula for the angle in standard position, remember, we're talking about this angle right here. That's the direction angle. This isn't the formula, but it's close. So I'm going to put a big asterisk here. And I'm going to say, we're going to use that formula, but we've got to be a little bit careful with it. Can anybody tell me what this has to do with getting the answer for this right here? What does this answer have to do? We haven't done anything wrong. What does that answer have to do with getting that answer right there? What is it? It's the reference angle. It's the size of the reference angle. Now, reference angles are always positive and acute. What this just did is it measured. Remember what tangent inverse does? Tangent inverse just gave me this angle right here. It told me that that angle is negative 60.94. So the reference angle is 60.94. So how do I find this one if I'm in quadrant 2? Yeah. Subtract it from 180. So the answer on this one is going to be 180 minus 60.94. So my answer is going to be approximately, what is it, 119.06? 119.06 degrees. Okay? So there are the answers. So put an asterisk by this and write reference angle. That's what it's going to give you. Formula works perfectly. It's just going to give you the reference angle in every quadrant except for quadrant 1. You have to use your noggin to figure out quadrant 2, 3, or 4 if the vector happens to be in those quadrants. Okay, any questions? Pretty easy? Okay, good. Then example 5 asks us to do something slightly different. It says, find the component form of vector v if the magnitude of the vector is 5.6 and the direction angle is 212. So, the magnitude is 5.6 and the direction angle is 212. Well, let's stop and think about this for just a second. Okay, before we were always finding magnitude and then finding direction angle. If we're going to do this in the opposite direction, it should make sense that first of all, we've got to figure out, well, what direction is this vector pointed in? From standard position, it's 212 degrees, so it's headed off here. And how long is it? 5.6. Our question is, what's A and what's B? That's what we want to know, because we want to put it in component form. Now, does anyone have any ideas on this? Jordan? Sine and cosine, because we want to find an opposite side and an adjacent side, and we have the angle from standard position, right? The angle from standard position is 212 degrees. Now, what type of answers are we expecting for both of these? Positive or negative? Negative, because we went to the left and we went down, right? So if I want the A, that's the horizontal, that's with the X. Am I going to use cosine or sine for that? I'm going to use cosine. So A is going to be 5.6 times the cosine of 212 degrees. And again, the reason for that would be that is the adjacent over the hypotenuse should be the same as the cosine of 212. Isn't that right? So times both sides by 5.6 and I've got that. So in this case, tell me roughly what is the horizontal component? 4.75? Okay, so 4.75. And what would be, it is negative, thank you, okay? And what would B be? It's going to be the 5.6 times the sine of that direction angle, the sine of 212. Okay, and if you type that in your calculator, does it give you a negative? And is it very big, or should we expect something kind of small? Something kind of small. And what is it? Negative 2.967. Okay? So, in component form, this would be negative 4.75, comma, negative 2.97, we'll call it. There's component form for that particular vector. That vector whose magnitude is 5.6 and whose direction angle is 212. Any questions? Okay. So knowing that we took the magnitude and multiplied it by the cosine of the direction angle to get the horizontal component, and that we took the magnitude of the vector and multiplied it by the sine of the direction angle to get the vertical component, can you think of a formula that would give us, I mean, if we have this information, magnitude and direction angle, that would give us the component form of the vector? Okay, so we'll do magnitude of V times the cosine of theta. And what would this one be? Magnitude of V times the sine of theta. Now, does that look familiar at all? Do you remember the unit circle? Okay, didn't we say the coordinates on the unit circle were always cosine of theta, comma, sine of theta? And that was if the radius was 1. So if I put a 1 in front of each one of those, that's the unit circle. If I put a 2 in front of each one of those, that would be a circle that has a radius of 2. And in this case, this just has a radius of 5. And can you see why we call that a radius vector if it's in standard position? Okay. Any questions? So all this is an enlargement of the unit circle, or a shrink of the unit circle. If it's bigger than 1, it's an enlargement of the unit circle. If it's less than 1, then it's a shrink of the unit circle. Okay, any questions there? Okay, let's see if we can get done with these next couple, and then you can do a lot of the problems on the homework assignment. Okay, let's talk about scalar multiplication. It's relatively easy. We're going to take a scalar, remember, a plain old number, and all we're going to do is basically distribute. When we multiply by a scalar like this problem right here, we're going to distribute this through, and what's going to happen is it's going to turn this into 6, 8. Whoops, make that look like an angle bracket. So it's going to make the vector longer. It's still going to go in the same direction. It's just going to go twice as long in that same direction. So twice as far in the horizontal, twice as far in the vertical. It'll still be in exactly the same direction. It'll just be twice as long. What do you suppose the negative 2 is going to do? Yeah, the negative is going to make it go in the opposite direction, and the 2 is going to make it twice as long. So this would be negative 2, comma, negative 2. If you think about what that would look like, this is what the original one would look like. And that's what negative 2 times the original one would look like. Okay? And what does just the negative do? All that does is move it the opposite direction. That's all it does. Okay? Any questions? Okay, that's called scalar multiplication, and I'd like to try and do these two problems before we leave. Okay, so this is called vector addition. Okay, and this is where it starts to get a little bit interesting and where we can actually apply these. There are a couple different ways that we can add vectors together and get what we call a resultant vector. So if somebody says resultant vector, it's just the result of adding or subtracting or doing scalar multiplication with some vectors. So we can do this using the tail to tip method, or we can use something called the parallelogram method, or we can just add them in component form. So I'm going to do this one problem and I'm going to do it 3 different ways. So here's vector u and here's vector v. I'm going to do the tail to tip method. So if I have u plus v, the first thing I do is I draw u. So u is 2, 3. So 2 and 3. So here's u. The tail to tip method works like this. I take the tail of the second one and I start it at the tip of the first one. So this is 5, negative 2. So I'm going to change colors here. So from right here, I go 5, 1, 2, 3, 4, 5, and then I go down 2, right here. So this is V. Now, here's the resultant. The resultant goes from the tail of the first one to the tip of the second one, so this vector right here is u plus v. Now, geometrically and graphically, we just did that problem. And you have some problems on your assignment that literally say, draw this problem. U plus V. There's U, there's V. This is what I get when I do U plus V. Okay, so that's called the tail to tip method. Okay, the parallelogram method gives you the exact same result, but it looks like this. I'm going to take a copy of V and I'm going to put it right here. Okay, so V is 5, negative 2 over 5 and down 2. So here's what V looks like. I'm going to take a copy of U. I'm going to draw it in standard position as a position vector, and then I'm going to copy it over here. So you'll notice the tails start right here and the tips end right here. If I use a parallelogram, the resultant is the diagonal that goes from the tail of both of them to the tip of both of them. Okay? So geometrically, you can represent it that way also. I kind of like the tail to tip method because I don't have to draw as much. Okay? And the last method is to just do it using components. Now take a look at this. Where is this point? Go ahead and count. Where is that point? Isn't it at 7, 1? Okay, so that point is 7, 1. It started at 0, 0 and ends at 7, 1. So wouldn't, in component form, wouldn't the answer be 7, 1? Okay, watch. What do you get when you take 2, 3 in component form and add it to 5, negative 2 in component form? Well, I add the horizontal components, that gives me 7. I add the vertical components, that gives me 1, and isn't that the answer? Okay. Any questions? So, be familiar with tail to tip, be familiar with the parallelogram, and be familiar with the fact that you can actually just do them using components. Okay, let me show you one quick thing, and we'll pick up right here, but I just want you to know this. What if I did U minus 2V? Well, if I were to do this using the tail to tip method, I draw U. There's U. What would minus 2V be represented as? 2 of these going in the opposite direction. So I would go back 5 and up 2. There's a minus V. And I would go back 5 and up 2. There's another minus V. And where would the resultant be? Start here and end right there. The hard part about doing this geometrically is you've got to count really well. Your graph's got to be really good. Okay? So we'll pick up right there next time. You've got enough that you can get started on the assignment. We'll finish this tomorrow, and then you can work on it over the weekend, okay? Any questions? Yeah.